Hello everyone, welcome to AJJ Engineering. Today I would like to discuss with you about molding of threaded components under mold technology. Purpose of threads in plastic. Threads are used in plastics for the purpose of assembling the components. Modern molding methods allow molding of external as well as internal threads. Threads in plastics part may be obtained by the following methods. 1. They may be tapped with a self-tapping screw or using a normal tap. 2. They may be molded into the plastic. 3. They may be part of metal insert molded. 4. They may be part of metal insert press fitted or glued or welded after molding. Molded thread is a form of undercut which may be external or internal. They may be molded by any of the following methods. Molding of internal threads. 1. Single interrupted thread design. 2. Forced stripping design. 3. Split core design. 4. Fixed core design. 5. Loose core design. 6. Collapsible core design. 7. Rotating core design. 3 types. Axially fixed rotating core design. Withdrawing rotating core. Axially fixed rotating core with extract plate, stripper plate design. Rotating cavity design. Single interrupted thread design. Single interrupted thread design is used for hollow circular components with a discontinuous single thread in line of ejection. In this case, the parting line of two core surfaces should pass through the starting and the end of the thread. The butting surface may be stepped. Box type components cannot be molded by this method. Forced stripping design. If the thread depth is less and the material is flexible enough, the component may be forced stripped using the conventional stripper plate ejection mechanism. Conventional V or square threads cannot be molded by this method. The component should be free to yield out while the stripping ejects it, and as such, only flexible materials can be suitable for this process. In the below picture, we can see that the component can be stripped with a stripper plate design. The stripper plate will move towards cavity side and the component from the core can be ejected out. Split core design. In this design, the split core moves towards the center during ejection, thereby releasing the threads. In the picture, you can see that when the ejector system moves forward, the molding inserts takes an angle movement which will become as a collapsible form. Then the component can be taken out. Fixed threaded core design. In this design, the component is removed by hand after molding. This is a low production method where once the cavity of moves manually, the component unscrewed from the core. Loose thread inserts. In this case, the component is ejected along with the threaded core and later it is unscrewed. The provision provided in the mold for the location of the loose threaded core should be approximately selected. In the image, you can see that once the cavity opens, the component ejected with inserts. Later, the insert is removed from the component. Collapsible core design. The collapsible core is a major breakthrough for molding plastic parts requiring internal threads. The patented design incorporates only 3 moving parts which utilize conventional mold movement. In addition to being automatic in operation, the collapsible core makes it possible to produce parts that until now have been considered impossible to mold. Parts with internal protrusions, dimples, interrupted threads and cutouts can be economically produced on a high or low volume basis. For conventional threaded parts, the collapsible core could cut the cycle time up to 30% when compared with unscrewing or other complex actuating mechanism. The basic principle of the DME collapsible core is illustrated in the figure. The assembly consists of 2 primary parts, a center core 1 and a collapsible sleeve 2. The collapsible sleeve is slotted through the greater part of its length, forming a number of individual segments which are of 2 different sizes. The smaller segment is marked as A and the larger segment is B. The segment A is tapered towards the segment B is tapered inward with respect to the center. These collapsible sleeves fixed on the ejector plate act like a collets. The center core pin fixed on the base plate expands the segment outwards when the mold is closed. During ejection, when the segment portion which comes out of the core pin collapses towards the center, thereby releasing the undercut. Collapsible mini cores. Collapsible mini cores broaden the application of collapsible core molded for closures as small as 13 mm. Due to the smaller diameter involved, these mini cores employ 3 larger collapsing segments combined with 3 narrow, non-collapsible blades which are an integral part of the center pin. As of a result, up to 80% of full threads or undercuts can be molded. The function of the collapsible core also permits threads to stop at any point along the molded length and the thread need not run out to the top of the core as with unscrewing mold. If a seal is required in the top of the closure, an undercut action also permits a longer threaded area to be formed without adding to cycle time or requiring long rack and pinion mechanism. In addition to threads, other configurations such as dimples, cutouts or protrusions beyond the capability of unscrewing molds can be successfully molded. These standard sizes of collapsible mini cores available are 13 to 16 mm range, 17 to 20 mm range and 21 to 24 mm closures. This image explains how the collapsible core is working. Rotating core design. Two major category of construction comes under this heading. In either case, The principle is that the core is rotated so as to unscrew the thread in a systematic manner. It can be done type A axially fixed rotating core, type B with drawing type of rotating core, and type C axially fixed rotating core with extractor plate. Axially fixed rotating core. For components having outside profile which prevents the rotation of the part inside the cavity can be molded by this method. In this case, just like the principle of removing a bolt from a nut, when is prevented from rotating, it can be given an axial movement. The core is rotated at any speed, no restriction, and automatically the component will come out of the cavity. This method may not be practical when the outside profile does not suit the operation. The length of the thread should be less than the cavity depth so that the cavity surface lock the component as it moves axially forward. If the length of the thread is too less compared to the cavity depth, additional ejector pins through the core pins may be required to eject the part. Withdrawing type rotating core. The principle of this design is that the threaded core is unscrewed from the molding by progressively withdrawing the core through the mold plate as it is rotated. When we rotate the core by one revolution, it moves out of component a distance equal to the pitch of the thread. Thus, in our mold design, we must arrange for the threaded core to be withdrawn through the mold plate at a distance equal to lead of the molded threads for each revolution of the core. This is achieved by guiding the free end of the core in a thread of the same pitch on the component for a single start thread. For multi-start threads, the guiding thread should have pitch equal to pitch times number of starts. This type of design is used when there is no external profile to lock the component inside the cavity during core rotation, or when there is no sufficient holding at the final stage due to the thread starting very close to the face. Here the rotation of the component is prevented by the friction created between the bottom face of the component and the molding surface as the component tries to go along with the withdrawing core. The adhesion between the component and the molding surface is generally enough to prevent the rotation of the component. However, it is better to provide rough surface or some serrations to make more positive. Figure given above explains the principle. The spur gear is rotated by some means making thread to unwind. The axial movement of the core shaft is controlled by threaded bush which has got the pitch equal to the lead of the component threads. A considerable force may be applied to the operating threads of the core shaft by the melt, and therefore the square threads or buttress thread should be provided at the rear end to withstand the applied force. For small diameter components, V-threads may be used. Screw jack system. The screw jack system consists of externally threaded jack pin and internally threaded spur gear. Movement of a rack or other mechanism rotates the spur gear at the same as the core shaft. The spur gear also prevents the rotation of the jack, which causes the axial movement of the jack pin. The jack thread is made of the same molded pitch. Thus, the stripper plate is moved by jack pin in relation to the core rotation. Cam bar system. This system consists of two bars with angle mating each other. Downward movement of the cam bar causes the stripper plate to operate as shown in the figure. The angle of faces depends on the rate of movement required. Rotating cavities. When the gate marks are not allowed on the outside surface of the component, this design may be considered. This design requires 3-plate mold with fixed system made through center of the core, which is mounted on the cavity of. The rotation of the cavity inside starts as soon as the mold opens, preventing the rotation of the component inside the cavity. The component having been unscrewed from the core remains in the cavity is then ejected from the cavity using normal ejection method. It is important that the mold opening be synchronized. If the mold opens too fast, more than the advancement of the component will be pulled out of the cavity. If the mold opening is slow, less than the advanced movement of the component will jack open the mold. Power and transmission system. The actuation of the core shaft can be by different methods as shown below. One manual. By chain and sprocket transmission figure 1. Chain power system. By rack and pinion mounted to the mold house figure 4. By screw and nut figure 5. Hydraulically pneumatically powered system figure 6. Layout of impressions. The layout mainly of 3 types. One is pitch circle layout, inline layout, and then 24 cavity layout for rotating core molds. Basically multi-cavity layout. Molding of external threads. External threads may be produced by following methods: fixed cavity design, post-stripping design, split cavity design, rotating core design. Fixed cavity design. It is the simplest form of producing externally threaded components. In this case, thread is directly machined into the cavity inserts. When the mold opens, the component is retained in the cavity. The component can be removed by rotating the part, so the part should have grip for holding or space for inserting a tool. Post-stripping. Thread may be post-stripped from the cavity provided the material is flexible and the thread geometry has rolled edges. Split cavity design. Threads can be easily molded using split design. When the splits are opened, the part can be easily ejected. Care must be taken to see that the thread form does not create an undercut profile in the split opening direction. Rotating core design. This design is same as rotating cavity design used for molding internally threaded components. But for externally threaded component, the cavity is fixed whereas the core is rotated. The mold is first opened at P1. At the same time, the core is rotated in a synchronization with the opening. As the component is being unscrewed, the second opening happens between the floating cavity and the feed stripper plate. It is essential that some profile should be there on the core which prevents the rotation of the component on the core. Some rough surface or small serrations will give sufficient holding. Thus the component goes along with the core from which it is removed.